and we have a value for quantum expression of gravity, instead of the Planck scale being the fundamental scale for understanding quantum phenomena, the neutron scale is the proper scale for understanding. And it's from that all other questions about the nature of quantum mechanics and quantum properties should be investigated.
Hello. In this podcast, Martin Gibson lays the groundwork for his unified theory of physics called natural mechanics. Natural mechanics is a beautiful theory because it models geometrically and classically the fundamental particles and their interaction with the fabric of space. All you need is really some basic calculus and a background in general relativity and quantum mechanics to understand how profound this theory is. It backtracks physics and rethinks the way that we examine the world. With mathematical precision, it can describe quantum gravity, which has been the treasure that physicists have been seeking for the past century. It demystifies quantum mechanics. It provides a geometrical basis for everything that we're seeing. It unifies all the fundamental forces into one. It can describe particle spin, tell you what it is physically, not just mathematically. The entire physics community needs to pause, examine this theory, and maybe even attempt to dismantle it. I am not yet qualified to make the following claim, but I am compelled to do so because of what I have seen. Look into this theory and give Martin his Nobel Prize. Hello, Martin. How are you doing?
Good, Serghei.
All right. I have been following your work for quite some time now. And what really caught my eye was an initial formula that I saw, which is your double stress tensor, which dives into unifying gravity into a quantum mechanical sense. But I'll let you introduce your theory. If you could please, let the audience know what's your theory, what it is about, and I guess how did you conceive of it?
It is a type of we're calling it natural mechanics. Basically, it's a wave mechanical view of nature at the scale of the emergence of rest mass particles. So in a sense, it can be formulated within certain aspects of general relativity if you accept space-time as having an inherent inertial component as a wave-bearing field. So it's a field theory. There are no fundamental, from a philosophical sense of ontology, which means something that it is the basic thing from which everything else is expressed. This is a field theory. So the ontology is that of a field. That's an inertial field.
How do you imagine the universe? What is this? What is this field? What are the different manifestations within that field? And how do you think about that?
I think of that field as being it's an ontological fact. In other words, the universe, without going into whether it is infinite or just indefinite, it is certainly indefinite in the sense that, as far as we can see to date, we can't observe where it terminates. There's no edge at the end of the flat Earth universe, and so it's just from that sense, whether it started as a Big Bang. I mean, there's ways you can model it as whether it's a Big Bang aspect of a deeper ontology, a deeper multidimensional reality, or or whether it's already always expressed the way we find it now. To me, neither of those are important. They are speculative. They are because there's no way to prove one or the other. All proof consists of is coming up with a logically consistent and coherent framework within which we can view what to me is the real subject of interest, which is what is the nature of fundamental particles. There's that component of there's the fact that everything seems to be comprised or is divisible. The question comes, at what point is it no longer divisible? At what point do we encounter the basic fundamental building blocks from which things appear to be made? And so that has been my focus starting over almost 30 years ago. Well, it's always been something of interest to me as long as I can remember. But when I started investigating it just to try to see how gravity and the quantum world were tied together, I did a basic a setup of analyzing, trying to see how gravity operated on that fundamental level. So there are certain parameters that science has established as being valid and consistent in different approaches to the subject of nature. What we're doing is investigating nature, obviously. And one of those, as we can see here, there are three basic invariants or constants that appear to be valid at any scale, and those are the speed of light, c, h bar, which is the reduced constant of Planck's reduced constant. It can be understood as both a form of action and angular momentum, and we can go into action at some point if we like. But it's a different way of looking at motion, of dynamic motion, meaning motion which has a component that is understood to be constrained by mass or inertia. And then we have G, Newton's gravitational constant, which derived from Newton's laws of motion, and who was also one of the co-founders of differential and integral calculus, which is necessary from this perspective in analyzing this whole subject matter. So those three constraints are generally acknowledged in scientific circles. How they fit together is not so recognized. H bar is made of, it has three basic properties that go into making and creating action or angular momentum. One of them is mass. One of them is displacement or distance length component, spatial length component, and one of them is time. And in what you're seeing here in the presentation, we assume that at some level there is a fundamental unit of that particular property that can be understood in terms of that unit as a unit basis for what we see in the composite world of material reality. And so if we look at 2, for instance, h bar is comprised of mass times distance squared. And instead of time, which is in the first or second term of the equation, we can look at the third term, which is the angular frequency. Or in this case, it ends up being angular frequency, but in any case, it would be a frequency of time, of the standard units of time, with respect to what we use now as SI terms or properties. So those, and if you look in whatever we shown here, the subscript alt indicates a unit value of that property. So it's a unit in terms of that natural unit, but in our world in which we observe it, it is scaled by factors so that those unit values in the middle of this term of O2 end up being 1.054 times 10 to the minus 34 kilogram meters squared per second. And so that kind of thinking and comparison, because unless you can compare your framework that you're creating mentally to some observable reality, then you're playing Dungeons and Dragons basically. No, unless it compares to something we can all agree is objective facts, then it's a interest maybe, but not real value in terms of what we're trying to do here, I guess. What I was trying to do when I started on this quest. So if you look at 4, you see that since in terms of unit values, the speed of light can be expressed as distance times the frequency here. And so if you look at that in terms of O2, you see that the mass and distance values can be expressed in terms of the speed of light, since that's a measure of distance and time in one sense. And you get doing that, you can plug C into H bar, and you can either see that on some fundamental level, which is yet to be determined in this modeling, mass is equal to H bar over the speed of light times the distance corresponding, whatever that corresponding distance is. So that gives you a fundamental unit of mass. That then can be substituted into G. And if you look at G, or the gravitational constant, which is once again an empirical determination, but it necessarily, if it has any basis has any structural basis in what it's doing in Newton's gravitational law, then it must of necessity be comprised of these same unit values. And so if we do that, we can take the mass where in the second term of O3 we see is or the fourth term really, where we've got R sub alt over M sub alt times C squared. We plug the mass value into that and rearrange. We can, I can probably the middle term is what we use. If we plug all the mass values in there, we end up with G being expressed as R sub alt squared over H bar times the speed of light cubed. So if we want to unpack what 5 means, or scroll down, if we do that and then rearrange so that we know C squared, we know C, we know the value of C, we know the value of H bar, and we know the value of G. So based on that, we can put all the distance, this fundamental distance value, on the left of the equation and solve for it, and we get a value of 2.61 times 10 to the minus 70 square meters. Take the square root of that, and we get 1.616 times 10 to the minus 35 meters. And that value is, by virtue of this thinking, indicates that value is the fundamental value of distance, measure of distance. Beyond that, you could still have links less than that, but in terms of them relating to the rest of these other 3 terms, that's been taken as being a fundamental value of distance, and that is called the Planck length, and the Planck area is above it in O6. We can also, going back, if we had, and you don't have to go down, switch up again, but if we went back to the previous discussion and solve for R instead of mass and plug that into the same equation for G, we would end up with 4.737 times 10 to the minus 16 kilograms squared, whatever that means. And if we take the square root of it, we get 2.176 times 10 to the minus 8 kilograms, which is for a particle, for a fundamental unit of mass, that's a very big particle. You think that on the scale of fundamental particles, electrons and neutrons and protons, they're more like almost in the neighborhood of 10 to the minus 30 kilograms. So it's quite a bit of difference. We'll see in a minute what that really is. So this has been the basis. This analysis has been the basis that has driven theoretical thinking in physics, as far as I know, for the last 100 years, or really somewhere around there. Whenever H bar was determined, I think Planck first determined the value, and I don't know if it's Planck or one of his cohorts, but they determined Planck's constant is that times 2 pi, which is, and then dividing by 2 pi gives you the H bar, which is more accessible in some sense analytically. But without going into that, if you scroll down, that's where things have stood, but it doesn't really. The problem is at the scale of the Planck measurements, these values are unaccessible. We can't. There's no experimental methods that we know of that can directly, or even since all of this is computationally driven, there's nothing that can clearly access 10 to the minus 35 meters. It's phenomenally small. So as a result, we've gotten the development of things like string theory and other concepts that have tried to figure out what's going on at that level. But there is an alternative to that. And if you'll go back up to the top again, yeah. Well, and the key thing is that all of these were derived at different points in history. Like G was understood by Newton, but it wasn't derived by him. It was empirically verified, I guess, or they kind of honed in on it with the Cavendish experiment, as I understand it, which was, I don't know, sometime after. I'm not real good on chronology of some of this, but it was, I'd say, 100 or so years after Newton. And then H bar is, or C was defined, or it was realized. They did this experimentally using just light and by various methods of measuring the speed of light classically. And then when, as I understand it, when Maxwell did his work, and then it was Heaviside, I think, after him, that really put the formulas of Maxwell into 4 basic forms relating electrical and magnetic phenomena as electromagnetic. In the process of doing that, Maxwell recognized that electromagnetic waves were really light waves, and that it corresponded to all electromagnetic radiation. And so that's where C was eventually verified or determined. Now, the value, where I say defined exactly, that's because they've agreed scientifically to key the second to that number of meters, or vice versa. But they've tied one to the other. So 1 second is perceived to be exactly that many meters, although whether a meter changes with the expansion of the universe, that's a different question, but we won't go into that right now. But so, and then H bar, as a measure of action, through as they got into various experiments involving particles, electrons primarily initially, I guess, as far as I know. I mean, they were obviously encountered first. They gave us the concept of spin, and when it's realized that spin has the same dimensions as shown here as action and angular momentum, or spin angular momentum, then it became associated with Planck's reduced constant. So now you can go from there. I guess we can go down. I'll say one other thing that of interest to me, and this, I didn't realize this at first, but this is something that through the analysis over time became apparent, is that if you divide this h bar by the speed of light, you have both of which are assumed to be constant, and you have a third invariant, which I'm calling tau, which is an inertial constant, and it's of the dimensions mass and length. And that the important thing here is that is not time related. If you notice, by dividing h bar by c, it gets rid of the property of time. So that's something that presumably is going to be invariant at any scale, any time, any place, any time. But how I got to this line of thinking, I think bears just a little bit of aside, and that's back when I've been interested in this when I was in college years ago. This is back in the 60s, but for a number of reasons, I ended up going into the field of economics, and then the field of my dad was an engineer, and so I went to work with him doing construction and design and construction work, and he was a structural and an electrical engineer, so I got hold of some of my learning from him. But in any case, back in, I guess it was about the mid 90s, I thought, well, I'd always been put off by the fact they couldn't graphically picture on the quantum level what was going on. And I've always been a visual person. And so based on that, I wanted to just understand it. So I knew that these particles had both wave and body configurations as far as the way they were modeled. And so I said, well, if you put two fundamental particles together and of a fundamental mass, you can, and use G, you can arrive at what that fundamental force is, gravitational force is. And so that's something I did. That got me thinking in these terms. So then let's go back to tau. In terms of tau, we can now formulate mass and length in terms of tau instead of h bar, understanding that you can intersperse one or the other anytime you want to. But then if we look at Newton's gravitational law, which is in 14, we realize that on some fundamental level that that force of gravity should be an expression of that fundamental whatever the fundamental force is, which I'm showing is T sub SI, times the quantity, and that quantity is not, that's a number which is arrived at by multiplying the mass, the number of bodies of two bodies of mass and dividing by their fundamental length. And you probably need to scroll down to see how that.
Okay. And just before we move on, that tau,
Okay.
that is a constant that you're introducing, and it's unique to your theory, but it is a well understood concept in physics because you can derive there. But I think what's not really explored or used very often is it as a constant. And so when you look at that m sub naught, that m0 r0, what that is rest mass, and r is length. So that's the reduced Compton wavelength of a particle. And so if for the audience here, if you want to do this exercise, multiply any rest mass of any fundamental particle times its reduced Compton wavelength, and you will get the same number over and over.
Correct.
And I've looked into this, and it is just not really acknowledged. Obviously, you can get there by dividing h bar by c. And these relationships exist, but I haven't seen it explored in bodies of work. And so, but you've honed in on it, and you do recognize it as this ratio that exists, as this constant that exists.
But I think the reason for that is there's been a preoccupation for the last 100 years with energy rather than mass. And so energy is, even though this analysis will clearly show that rest mass energy equivalence is well defined. The energy in general terms is thought of as being this property that is what it really is a measure of activity, but it's seen as of both a potential and an actual or kinetic form, but it's seen as conceptually as being something fundamental rather than being a measure of something moving. It's seen as a thing in and of itself, and I think that's been part of the delay in making these realizations.
The 0.13 here. So essentially, what you're doing is you're saying we can rethink the fundamental mass from what we saw above, which was the 2.176 times 10 to the negative 8 kilograms, and we can rethink it in these terms because you have this fundamental ratio between rest mass and Compton wavelength of any particle. And so if you put it like this, you can derive the fundamental mass as 1 over the fundamental length times this constant. Okay, so now we've done that, and this is 0.14 is Newton's gravitational formula. And could you go over the rest of this? What is 0.15? What is that formula saying?
That's saying that if Newton's gravitational constant, as we'll see, is obviously a composite form. It's made up of actually it requires 2 units of mass. G has to have can be broken down with a numerator, which is units of mass squared on the bottom. The denominator. The numerator will be units of distance squared, and what that does is plus or times, I should say, times whatever the fundamental force of gravitational attraction is. So if we do that, what happens is that, and you can see that in 16, what it does is it breaks down the capital M1, M2 values of groups of mass as and classical distance, it breaks them down into the numbers of each of those times what is, if such exists, it is times a value which is a quantum gravitational force, T, which is tall sub alt G in 16. So 15 just says that tall sub SI value in SI terms is something unknown that we'd like to determine, and so that's where we end up with 16. So that tells us, therefore, in 17, that the quantity, and it's not the quantity of units because it's the units divided by their distance in terms of natural units. But if you take, in other words, if you divide, the distance squared, units of natural distance squared divided by units of mass squared, you have a value that will be used, which is invariant itself, based once we know what those values are, and that times whatever the t sub dt. When the last terms of 17 is a differential, we see that we've shown that as a different differential form, which we'll get to in just a second and derive that. But that gives us G. So if we look at the last term of 17, G equals, and you look at the last term, R sub alt to the fourth over tau squared times this differential. So if we can determine the differential of d tau sub alt in terms of R, then we'll end up with one value that we can solve for, because we'll know what tau is, we know what G is, and that together we can solve for that, and that should tell us what the value of R sub alt is, not in terms of a Planck scale, but in terms of whatever defines the gravitational constant. So does that make sense, or do you have any other questions at that point?
So that tau, which is that little t, that's essentially what you're saying is the actual differential force of gravity.
Right.
That we're trying to, that you're isolating in order to in order to try to get it out of or to separate it from the fundamental length and mass and everything else, so that we could derive the fundamental units of length and mass. Is that, did I get that correct?
That's correct. Although it is gauged to whatever R sub alt is. If this is to have any verifiability, then what we should end up with is the delta tau sub alt should be expressed in terms of R sub alt in a manner that will show that is a natural, R sub alt is a natural gauging value in creating G, and then that is used in gravitation.
And
so
the R sub alt, we mentioned it earlier, but what you're saying there is that there is a fundamental unit of length. That fundamental unit of length is then tied to the differential force of gravity. So meaning as it I guess compounds, so will, or is that correct to think, as it compounds, so will the force of gravity?
Yes, I mean it's expressed on that level is a force, and we'll see that it's centripetal force, which means it's in terms of fluid mechanics or field theory, it would be the divergence of the force, convergence in this case, really, because it's centrally located at whatever form is driving is creating R sub alt is also creating gravity at the same time, based on this analysis. So if we go down, it leaves us next. We need to define delta tau, and that is really pretty straightforward in terms of if you take the total derivative, which means if you think of a stress as being a partial derivative of force, which is indicated by tau sub alt, over an area, A sub alt. Those are differential values. If you take the whole derivative, and without, I don't want to go too far into the calculus, but it's pretty straightforward. If you do the differential is shown, the whole derivative is shown in 19 as a change in force, change in stress equal to the change in stress as a result of a change in force, and a change of stress as a result of a change in area. So those two variables and give you that. And if you solve 20 as the final solution of the partial differentials, which is straightforward, and that gives you then, and let me step back up to 18 and explain 18. And the paragraph above that will tell you how that's derived at. But basically, if you think of T sub alt as being a four-dimensional stress energy tensor, and these tensors, tensors are normally structured or on a point in space-time, or a point in whatever manifold you want to express it in. It's expressed as a direction, as a vector potential, or potential for any change to occur in a given direction with respect to 3 or 4 dimensions. In this case, T, capital T, is a stress energy density, and it is really volumetric in that this change is in 3 dimensions. It's not just in one. So it's so we use a tensor, but it really the way to define that tensor is is isotropically from a given central point. And if we do that, then we see that for any given arbitrary cubic surface at the center of that tensor, you're going to have 6 of those 6 faces. So there's going to be 6 aspects of it, 6 components of the stress energy density tensor. And then the square root of 3 comes because if you were the resolution, not the resolution, what's it called? The value of, using Pythagorean notation, the square root of 3 is going to be the equal force in all 3 components would be at a resolved value at the square root of 3 from whatever tau is. So we can draw a picture for that. I've got them drawn elsewhere, but we can show that if we want. But what that means is that F, which is the stress on the surface of the cube, is going to be 1/6 times the square root of 3 of the total energy density stress within the sphere itself. So if that makes some sense. So from that, dealing with it with the a given surface in 19 and 20, and then down in 21 and 22, we can break apart equation 20 into the two components, and that gives us a change in force, fundamental force, with respect to the change in the energy density, as seen in 21. 22 does a similar thing with respect to the area. We'll deal with 21 first, because if you'll notice in 21, this is just basic dimensional analysis, A sub alt over 6 times the square root of 3, that A sub alt should equal R sub alt squared. So that now, as T dt sub alt, allows us to take 21 and plug it back into into 17 above, the last term of 17. Yeah, so now we can plug that into there. And then what we get with as a result of that, if you keep going down further, is you get a new expression for G of 23, which is R to the 6, R sub alt to the 6 times 6 times square root of 3 times Paul squared is equal to G. So now by isolating R on one side of the equation, we get a value where dt sub alt is is naturally normalized as 1, so that what we end up with is O24 is a value of R to the 6 of 10 to the 9 minus 95 meters. If we take the 6th root of that, we come up with 2.10 times 10 to the minus 16 meters. So that says, if our thinking is correct, that R sub alt should represent a natural scale at that scale, at 9.1 sub alt. And we can turn around and do the same thing with the mass by using TOV, and we come up with a natural value for mass of 1.674 times 10 to the minus 27 kilograms. Let's everybody take a deep breath.
Can you tell me what is the significance of this 2.1 times 10 to the minus 16, that it represents a natural, or rather a fundamental unit of length?
That is, yes, we'll do that right now. And also 26, because that's equally important. If you want to check your SI values, 25 is the reduced Compton wavelength of a neutron. And 26 is the rest mass of a neutron. So what this analysis says is that instead of the Planck scale being the fundamental scale for understanding quantum phenomena, the neutron scale is the proper scale for understanding. And it's from that all other questions about the nature of quantum mechanics and quantum properties should be investigated. And if we can go and we can solve using this, we can solve for d t sub alt, and we have a value for quantum expression of gravity as being 4.244 times 10 to the minus 3 newtons. We can plug now. If understand that all this has been said without any analysis of the structure of what a neutron might be, or what a natural structure, quantum structure might be that would generate these observable numbers. Because 25 and 26 are observables. They're not theoretically called out in any analysis that I know of from a fundamental perspective. So as far as I know, there may be other people who have done the same thing that I haven't read about, but as far as I know, this is the first well, I've been writing about this for 20 years, but it's not, this is the first time well, that it's been stated as being a emergent property and not something that is, anyway, that is, so there we got this for the neutron. This analysis, if we think of it in terms of vector potentials, or we could talk about fiber bundles or that kind of thing. There are different ways of looking at the same phenomena, but if we see it as a wave phenomena, then pulse subalbum 28 represents the wave force that's creating this differential at 27. So the wave force, once again, using the same foundation, is tau times the frequency squared, and that gives us a value of 7.6167 times 10 to the 5th Newton. To check this to see if we're in the right ballpark, we can take the ratio of the Newton of 28 to 27, which is the ratio for this fundamental wave force, which is also responsible for the strong force. Because if you think of waves as being you think of wind, it's like uplift on an airplane of airfoil. You got wind moving over a curved surface, it's going to create lift. If you have two that are moving in the same direction, then they are going to create a cohesive force to pull the particles together. And for that to happen, you've got to have one of them would spin up and the other one would spin down. And if you do that, if these are understood to be rotating oscillations, then it creates that force creates the strong force that pulls particles together. So the ratio there is in 29 is 1.68 times 10 to the 38. And that is the generally recognized ratio of the difference between the strong and the gravitational force. So this is once again confirmation of this line of thinking.
So just to
so I don't,
just
okay.
Sorry, quick recap. What you've done here is you've taken the known constants, you've rearranged them, you've made some assertions that G, the Newton's gravitational constant, is comprised of different components. You have isolated those components in order to try to understand what is the force and what is the other things that you can pull out. And by restructuring these, thinking of this as or analyzing it as a stress energy force acting on an area unit in space, you've derived a fundamental length, which is which happens to be the exact reduced Compton wavelength of the neutron, which in modern physics emerged from an observational experiment, which is why from the Compton experiments, where they scattered photons off electrons, and to understand what their wavelengths are after these collisions. And so you have that, and you can rearrange that in order to also get a fundamental unit of mass. And when you use these two properties, you can then derive this 4.244 times 10 to the negative 33 newtons, which, in other words, what people might recognize is the quantum gravitational force.
Correct.
And 28 is the value of the wave force. And that wave force is the wave that's responsible for what we observe as fundamental particles. And if you take that wave force over the gravitational force, you get this understood ratio, or not understood. You get this known ratio of 1.688 times 10 to the 38. But that ratio is not generally understood or derived from something. They just know that it's there. It's more like
It's empirical.
It's an empirical ratio, but you're deriving it here through these fundamental, by replacing the Planck scale with a more natural fundamental scale.
Correct.
Okay.
And incidentally, it's key to commenting on the fact that even though they have known what 25 was or 26 was way before now, none of this is used in deriving. All that's used are those three basic particles. Once they're understood to have a natural unit of some sort, of some property, of those three basic properties, mass, distance, and time. Once that's understood, and we get rid of time by using TOF. Once that's understood, we can create a theoretical model and look for what those fundamental R subalt and M subalts are. We didn't need to know Compton or any of the rest of that before then, because it's although obviously I did when I was deriving it, because I was trying to figure out what was going on. But when you go back, it's like reverse engineering something. You figure out what's going on, then you give it to somebody else to try to create, hands off, recreate it. The first part of this does that. It's a hands off statement of what those values might be, if you assume that it's a different that the force is a differential force, classically differential force. So,
all right, beautiful. So, ladies and gentlemen, we just derived quantum gravity. All right.
Now let's go down a little bit further.
Okay. Let's keep going.
And if we look at that, and we can also analyze in terms of the values of A subalt and of delta A subalt, and we see that delta A subalt is equal to 1.6 times 10 to the minus 70 meters, which is the Planck scale. But it's a Planck scale of a differential area as it relates to the differential force, and not as it's derived earlier using in the first part of this analysis. So that's important.
So what does that say? What does that say about the Planck scale, how it is classically treated, and how you think about it in natural mechanics?
It's certainly it's derived naturally, but it's not representative of a discrete scale. It's a differential scale. In other words, it could be anything. In fact, if you think of that particle as being spinning, it's going to go from moment to moment. It's going to go through fluctuations. What we're looking at is the average over time. So from a very small fraction of time over time, those delta A and then the force are going to vary within certain parameters. This is just basically, as I understand it, in other words. So it's not, but they're not discrete. They don't come in packets. In fact, I think the whole concept of packets of energy is misunderstood. If you think of a waveform as being, if you think of an oscillating fan, each time the fan comes through, it hits you with a certain amount of force. That force can be measured. and therefore is discrete. But it doesn't mean that the force itself is made up of packets of fan blown air. You understand? Does that make sense?
Yeah.
So,
And that A sub naught is essentially the fundamental area. So if you take the square root of that, you'd get the reduced Compton wavelength once again.
correct.
Right?
Correct.
Okay.
Correct.
So we can keep going here.
Yeah, and that's just a reiteration of okay. So it shows that the invariant stress of the initial condition is has the same ratio as is tall. I mean, it's probably not consequence. Okay, you can keep going down. Those are some various properties that we can compute based on just the notion of what a wave force or wave stress is or wave strain. That's something that's not normally considered in quantum mechanics or relativity, as far as I know. Is although in relativity we talk about a warping of space, which is a strain, and so a strain is a change in some, especially in terms of length, it's a change in some material with respect to its original physical condition. And that, incidentally, that wave strain is something that we can see and is tied to the Hubble rate. So it helps, because it's I think it's close to, and there's some other factors involved, but it's close to the square root of, if you take the square root of 33, it's something like around 10 to the 19th. And the inverse of that would be it's close to the Hubble rate, but it's more concise. It's beyond the scope of this particular presentation, but it is written up in the other papers. So let's go. Is there anything after this? I can't remember what I said. You can see, if you want to go back, just for a plug, if people are concerned and they've got the money, they can, or they can see my website and not pay the money. They can go up a little further. You see the reference to these compilation of them. As far as the values, yeah. The fundamental wave equation can now be expressed in terms of the wave number, right? I haven't gone into the wave number. Wave number is just the inverse value of a wave produced wavelength. So that's what K is in 15, or kappa sub alt squared. So that's really a wave equation of the inertial constant expressed in terms of kappa squared and omega squared. And from that, we can derive a Schrodinger equation, wave equation. And here I have instead of using psi for the wave function, which I think is associated in the public mind with probability calculations. Here it's understood to be deterministic, so I've used omega instead, capital omega. So, and I is a function of the fact that this wave has in the area, if you think of a stress as being a force operating towards, away from, or across a unit area, if you think of that unit area instead of being a square as being a circle, for instance, then well, it doesn't matter either way. But if you think of that in those terms, the imaginary or that area can be analyzed in terms of a complex as a complex plane. If you do that, then I is associated with that aspect of 15 AI, and so that imaginary sense indicates the rotational aspect of that aspect of the tensor. And as a result of that, well, it indicates torsion, really. So from that, we can also, what we haven't gone into here is how this basic neutron, first of all, we need to show the structure of that, which is done elsewhere, but we can talk about that sometime if you want to. The structure of the neutron wave, and then how what causes it to decay into a proton and emit an electron, and when that does, there's a missing mass of from that process, and that missing mass can be captured in the notion of this complex plane against which the stress is operating. Okay, if you look at that, that is what I'm saying is behind the nature of the missing mass of beta decay. And you'd have to read the whole thing to get a full grasp of it. But basically what it's saying is that natural logs and natural exponential functions, which are shown by the red curve here, and each of those on the right-hand side and left-hand side being the exponential and y sphere. Anyway, the slope of the line at E sub alt is a natural exponent, 2.718. And if you'll notice, the angle on that, the slope of the line, which is the derivative of the two, converges at the origin of this particular situation. The same thing, if you apply if you apply that same thing to what I'm calling E sub 2, which is, in other words, you can create a system of natural logs which varies along the whole slope of those two curves. The green one on the bottom and the blue one on the cyan on the top intersect at a point in the lower left quadrant, which is equal to, I believe it's 2, and each minus 2 in both scales. So those angles represent an origin that is displaced by that amount. And what it's showing is that for any change, a logarithmic change, which all of this expansion can be understood as a logarithmic expansion of the universe, all of that, if it uses E sub 2, it as an expansion force, the differential area is assigned to the rotational or the torsion aspect that occurs during beta decay, and it's that energy that is maintained in that torsion that doesn't show up anywhere in the observables. It's accounted for through this analysis, but it's pretty arcane. So you've got to study. It would take some time, but
yeah,
it's worth it.
All right, Martin, I think we can wrap it up here, just in the interest of time.
Okay.
So, question for you then. So you've been working this for a very long time. What do you want? I guess what's your ideal outcome out of putting your work out there? What would you like to happen?
I would like somebody to read it and critically in detail and not just say, huh, no. It just, I mean, it's accurate. I know it's sound. I've always been logically oriented. I don't, I'm not motivated, and I steer away from any kind of glitzy approach to finding new particles and finding, things that are, I mean, emotion doesn't enter into this. To me, emotion to me would be finding people that would read it and give me some critical feedback. That would be nice, just because I don't have any doubts about the validity of it, but uh, there's a lot of things that I don't know about the implications, things that I don't know at all about, and other implications that I have an inkling of, such as cold fusion or the notion of capacitive propulsion systems, and that kind of thing. Uh, there is, it would only benefit from an involved discussion with people that are willing, can see the wisdom in taking the time to pursue it. And I don't know how else to do it other than my presentation on on really analyzing the gravitational constant should be motivation enough for anybody in the field who has an understanding of the nature of gravity.
All right. We got to end it here. So thank
Okay.
you.
All right. Till next time.